In this video, we're going to be looking at an introduction to quadratic functions. So before we talked about quadratic expressions, so an expression is just something without an equation, without an equal sign. And if you remember and recall what a function is something that has a relationship between an x and a y. So it's a relation, and then it also passes the vertical line test. So we're going to be looking at taking our quadratic expressions and turning them into functions. So a quadratic function is still a second degree, so it still has to do with the degree of your polynomial. So it's a second degree polynomial function. And what's going to make it a function is if we had something like this, x squared plus 3x minus 4, this is just a quadratic expression. What would make it a function is relating it to y. And so we would do that by setting it equal to y. So the standard form equation for a quadratic function is just y equals ax squared plus bx plus c. We've looked at this a little bit previously, but a, b, and c are just real numbers, and the x's are variable. And if you plug numbers in to this, you'll get outputs of y, and then you now have your relation that gives you ordered pairs. So when we're looking at quadratic functions, the graph of a quadratic function is called a parabola. Parabolas, they have a very specific shape. They're kind of a U shape. They're U-shaped curves that are symmetric. So they have symmetry about some vertical line, and that vertical line we call the axis of symmetry. So mathematicians in naming things are not always super creative, but in times it helps because then it's very descriptive of what we're trying to talk about. But the axis of symmetry is the vertical axis in which the function is symmetric about. So one thing that is good to note when looking at a quadratic function is the leading coefficient tells us a lot about what's happening with our function. It tells us how tall and skinny our function is, but more importantly, it tells us the direction in which it opens. So if the leading coefficient is positive, then that means that our parabola is going to open up. It'll have a shape something like this. It'll be a U shape like this. And then you'll have your axis of symmetry here that kind of goes through the middle like this, that our graph is symmetric about. If the leading coefficient is negative, then our graph opens, down. And it might do something like this, and then you'll have your axis of symmetry here. Now, obviously, these are not very accurate because I'm not really taking a whole lot of time to try and graph, but these should be perfectly symmetric. If I were to fold the one side to the other, they should land exactly on top of each other when dealing with a parabola. So this is what their general shapes look like, and this happens when this leading coefficient, so I'm talking about this value here, the value of a, if it's positive, right? If it's positive, it opens up. If it's negative, it opens down. So let's go ahead and take a look at trying to identify some different times or different cases where our graph would open up or down. So if we're looking at this first example, it says determine whether the graph of the parabola opens up or down from each given equation. So really all we care about to determine this is the value of a. Now remember, a is just the coefficient of our quadratic term. So in this case here, there's our quadratic term. The leading coefficient, 3, is positive. So a is positive, which means it opens up. So again, here's a. It's positive, so it, again, opens up. A in this case, so a is right here. A is going to be -1 in this. So a is less than 0, which means our graph is going to open down. Graph's going to open down. Now, in this one doesn't look like the ax squared plus bx plus c. Really what's happening is we're missing that bx term, but we really could just think of b being 0. But again, that does not impact whether we open up or down. We just care about the value of our leading coefficient. Since our leading coefficient is negative, this opens down. Okay. what is the coefficient of our quadratic term here? Now, you might be tempted to say that it's -8. But remember, this, we can see that this is not in standard form. So standard form should go from the highest degree to the lowest degree. So really this should be our leading coefficient. So if we wanted to rewrite this in standard form, we could. But for this purpose, we just cared to determine whether it opens up or down. So I actually just want to know the coefficient there. So the coefficient there is 7, so it's greater than 0. So this is going to open up. Where's our quadratic term here? Our quadratic term is this last one. It's negative, it's less than 0, so it opens down. It opens down. Okay. So another important feature in a parabola is something called the vertex. So we've talked about the axis of symmetry. So this is our axis of symmetry, and it's the vertical line in which our parabola is symmetric about. If we were to fold across this vertical line, the left side and the right side should land right on top of each other. But this axis of symmetry goes through a very special point. So that point there and that point there, those 2 points, those points are called the vertex. The vertex. And the vertex of a parabola represents the highest or lowest point on our curve, right? It's the highest or the lowest point on our curve. And whether it's the highest point or the lowest point is dependent on whether our graph opens up or down. So we can see we have 2 different kind of shapes here, right? This is a parabola that opens down, and this is a parabola that opens up. If our parabola opens down, is our vertex, so our vertex is right here, is our vertex going to be a highest point or a lowest point? Well, if it opens up, well, this is it opening up. If it opens up, then that means that this point down here, the vertex, is a minimum. It's the lowest point on our graph. It's the minimum. And if our graph opens down like this, our vertex is a maximum. Okay? So let's go ahead and identify the vertex. And so when I say identify the vertex, what I mean here is write its ordered pair and then find the minimum or maximum value. So this is a key word here. Find the minimum or maximum value of our function. So in this curve, it opens down, which means we are going to have a maximum value, and it's going to happen at the vertex. So if we were looking at our axis of symmetry, the axis of symmetry would be that line roughly, right? This line here, that would be our axis of symmetry. The axis of symmetry always goes through your vertex. So what are the ordered pairs of our vertex? So you're going to do the x-coordinate first. So the x-coordinate is 1. Let's get rid of this thing. The x-coordinate is 1. And the y-coordinate is all the way up here at 5. So the y-coordinate is 5. Now, what is my maximum value? So I know that this is a maximum because it opens down. But what is its maximum value? Now, when we're referring to value, the value of our function, the value always talks about the y-coordinate. So what is the y-coordinate? What is the highest that this graph reaches, right? So that would be our maximum value. The highest that this graph reaches is 5. And that's basically the upper value, the upper limit of our range, if you remember domain and range. Okay, so in this one, it opens up, which means our vertex is going to have a minimum. Where does our vertex occur? So you can see the x-coordinate here is at -2. So at -2. And the y-coordinate is here at -5. So which of these did we say represented the value? Well, the value was the y-coordinate, so the minimum value is going to be -5 here. And then this last one, again, it opens up. So we're going to have a minimum. The x-coordinate here is 3, and the y-coordinate, it's not at a whole number. I just happen to know that it is exactly halfway, so the y-coordinate is 0.5. So what is our minimum value? Well, our minimum value is going to be 0.5. Now, do parabolas, like this one that opens up, do they have a maximum value? Does this have a maximum value? And because this arrow is telling us this is going up forever, and really these probably should have arrows on them too. These are going up forever, and these are going down forever. Can this graph that opens up have a maximum value? Well, the answer is no, because this is going up forever. And then this one will not have a minimum value because it's going down forever. So this is just kind of a brief overview of quadratics. This is going to be the type of function that we're working on for the rest of the year. And we're going to be looking at a bunch of different ways to solving quadratic functions. Now, one little piece of insight as far as what we're looking for when we're trying to solve. So when you want to solve a quadratic, what we're going to be looking for are where the quadratic hits the x-axis. So basically, we're looking for x-intercepts when we're trying to solve quadratics. So in the next lesson that we do, we're going to be looking at different ways to solve quadratics.